Welcome to this course on machine learning using Python programming. In the previous lecture, we have seen two different machine learning models, decision tree and KNN for regression purpose, and today we will see some other concepts like regularization and R square metric, that is very important topic in case of regression. So, we will see what is regularization and why it is needed. We discussed in machine learning models sometimes there are chances of overfitting. So, in that case your model will learn some noises also from the data set, or if some outliers are there, or you may say if overfitting is there, in that case your model may it will be working for the training data, but it will not work for the test data, or you can say for the future data your model's predictions will be wrong, or you can say generalization error will be very large in that case. And for that purpose, to reduce overfitting problem, we use regularization. So, we can say to prevent overfitting we use regularization. And how we do regularization? We add a penalty to the loss function that we use to optimize the model's coefficients. So, we have seen in case of suppose simple linear regression or multiple linear regression, your loss function was summation over I is equal to 1 to n, where n is the number of instances and or number of data points in your data set. So, then we this is suppose predicted response variable and this is actual response variable for all instances, and the square of this, and this is the cost function, and we try to minimize this function. So, this is called as sum of square error. In the same way, we can take any other cost function like summation I is equal to 1 to n, and that is mod of yi cap minus yi. So, this is called as absolute error, sum of is absolute error, this is sum of a square error, or so any we can use some other cost function also. What is difference between these two? Generally we use sum of a square error because this is differentiable in all the at all the points, and that is why if we want to use gradient descent method for optimizing this function, we can use this function, because we have seen that in gradient descent method we need to take differentiation of this function with respect to all the model parameters, while this function is not differentiable at one point. So, we can't use gradient descent method to optimize this cost function. So, that is why we generally use this cost function, and so when we can write this function, we can expand this cost function like this, I is equal to 1 to n, then what is yi cap? Yi cap is the predicted value of the response variable. So, that in case of simple linear regression it was b naught plus b1 x. So, this is y naught yi cap. So, this is for ith instance. So, xi minus yi. So, there is a point x1, x2, x1 y1, another data point x2, y2 up to so on. So, when we are taking this, we are defining this cost function. So, we can say that now we will take a square of this. So, in this way we have seen this way we define the cost function. And what happens, we are trying to find those values of b0 and b1 such that this cost function value is minimum. So, what happens, sometimes we learn those values of b0 and b1, or it will be better if we understand it with respect to multiple linear regression, where your model is y is equal to b0 plus b1 x1 plus b2 x2 plus b3 x3 and so on. So, in this case, when we will learn these values b0, b1, b2 and so on, we will learn these values from the data set such that this cost function is minimum. So, this cost function is minimum, and we are seeing basically on which variable y is depending more, or what is the relationship between y and all these independent variables, and this is given by the value of these coefficients. So, if b1 is less, it means y is depending on x, but there is less relationship, or x is helping less in defining the variation of y. If b2 is large, in that case we will say there is a large relationship between y and x2, and because this using this function we are taking this weight is more, weight corresponding to x2 is more, it means we are giving more weightage to those independent variables that are more important for predicting the value of y. And for all those independent variables where the coefficient is low, those are given less weightage in predicting the value of y. So, what happens, sometimes in case of overfitting, these variables, these coefficient values that are learned, these values are very large. These values are large because when we are learning, we are seeing x1 is important, x2 is also important, x3 is also important and so on. So, these coefficient values that are learned are very large values. So, what and then it is called as the overfitting. Some variable is not important, what we want, its coefficient value should be less. If this variable is not important in predicting this the value y, in that case this coefficient must be 0. So, but generally it does not happen. We always get some correlation between these variables y and xi, any xi, and that is why we get some value of bi's, at least it is not generally 0. So, this is and these coefficient values sometimes becomes large, and this in that case there is a overfitting. So, what we do, we use regularization. So, there are basically three types of regularization. One is L1 regularization, that is also called as lasso regularization. Second is L2 regularization, that is ridge regularization, and then elastic net. First we will see L2 regularization, that is ridge regularization, then we will see L1 regularization, that is lasso regularization. So, in case of L2 regularization, what we do, we give a penalty proportional to the square of magnitude of the coefficients, and we add this penalty to the loss function. So, your this suppose now I am writing this I am writing in terms of now theta, suppose theta. So, this is your cost function. So, cost function in that case is summation I is equal to 1 to n, and then h of, I am writing in this form. So, h of theta x, sorry, h of theta x I minus y I square. So, this is the loss function. So, here I can write it as y I cap. So, this is the predicted value and this is the actual value, and we are taking a square of summation, square of this over all the instances in our data set, and we will take average of this. So, we have seen we add here 2 also, and then sorry, n 1 by 2 n, and this was the cost function. But in case of L2 regularization, what we do, we add one term, we add one more term, and that term is square of magnitude of the coefficients. So, your coefficients are written here in terms of theta. So, there is a parameter lambda, and then summation, suppose j is equal to 1 to number of parameters are suppose m. So, you will take theta j square. So, here theta is nothing but theta naught is suppose beta naught, sorry, b naught, theta 1 is b 1, and so on. So, we can write, sometimes we write coefficient in as theta naught, theta 1, theta 2, and so on. Sometimes we use the notation beta naught, b 1, b 2, and so on. Sometimes beta naught, beta 1, beta 3, and so on also. So, what we have done, we in this cost function we added one more term, and now we are not only minimizing this, we are minimizing this whole function. So, in that case what we are trying to do, we are trying to make values of theta less, because we are minimizing this term also. So, in this way what we are doing, we are shrinking these coefficients, we are shrinking theta naught, theta 1, theta 2, and so on. We are shrinking these b naught, b 1, and all these coefficients we are also shrinking, trying to shrink, and in this way we are trying to reduce overfitting. So, this is L2 regularization, and what will be the effect? Effect of the L2 regularization will be that it will shrink these weights, or it will shrink these coefficients or model parameters. So, but in this case you can see it will not make them 0, because this is theta square. We are, if we will write here only theta, then it can be 0, but we are writing theta j square. So, when we are writing it theta j square, then definitely these parameter values will not be 0, but these are shrinked when we added this term in the cost function. So, we can say that it will smoothen the model and it will reduce the risk of overfitting by reducing the impact of less important features. So, the features that are not important, not much important, their coefficients value will be shrinked, and we can say that it will work very well when many features are there in your data set. And then suppose if there is multi collinearity problem in your data set, that time also it will reduce the coefficients of those features that are related with each other, and it will adjust coefficients of those features that are related with each other. So, this is the L2 regularization. Now, we will see what is L1 regularization. So, in case of L1 regularization, what we do? We add a penalty term, but here penalty term is different, and that penalty term is proportion to the absolute value of the magnitude of these coefficient, not the square of magnitude of these coefficients. So, your cost function is j theta. So, first term is same. So, that is 1 by 2 n, where n is the number of instances, I is equal to 1 to n, and I am writing it now y cap minus yi cap minus yi square. So, initially we were minimizing only this function. Now, we are adding one more term, that is lambda and then summation j is equal to 1 to m, where m is the number of parameters. So, and then theta j is square, sorry, not a square, in this case it is mod of theta j. So, in case of L2 regularization we have taken here theta j square, in case of L1 regularization we are taking mod of theta j. So, we added now this term, and again this term will help us to shrink values of theta j, but in this case even some coefficients may become 0, because we are not we have not taken square here, we have taken absolute value of theta j. So, what happens here? It will help in reducing overfitting, because we are trying to reduce this term also. So, your coefficient values will be less, even it can be 0. Suppose there are chances that in your data set some features may not be relevant. So, in that case it is better to use L1 regularization, because it can now make coefficients corresponding to those features that are not relevant, it will make them 0, it will make corresponding coefficient 0, while in case of L2 regularization we have seen it will not make it 0, it will only shrink these values. So, you can say that L1 regularization leads to sparse models. Sparse models means, since many of the coefficients can become 0 corresponding to those features that are not relevant, and that is why in your model will be like you can say y is equal to b naught plus b1 x1, but suppose x2 is not important. So, that b2 will be 0. So, that term we will not have, then b3 x3, and then suppose x4 and x5 both are not relevant. So, b4 and b5 will also be 0, then b6 and x6 and so on. So, in this way your model is a sparse model, and it is better because it is reducing the overfitting problem, because it is not now taking those features that are there in the data set, but not much relevant. So, this is L1 regularization or lasso regularization. So, we can say that this lasso regularization we should use if we have the idea that there may be some irrelevant features in the data set, or sometimes when your data set is having large number of features. So, if it is a high dimensional data set, and so you can say this lasso regularization can work as a feature selection method also. So, it will select only those features. How it will select only those features? By making coefficients corresponding to few features that are not relevant. So, in the final model you will have only those features term that are relevant. And now we will see the third regularization method, that is elastic net. So, elastic net regularization is a regularization method that is also called as a hybrid regularization method. So, it basically combines both L1 and L2 regularization. So, we have already seen what is L1 and L2 regularization. In L2 regularization case, we added one penalty term, and in L1 regularization case we added another regularization penalty term in the in our cost function. So, here what we do, again we add in elastic net we will basically add combination of, this is combination of L1 regularization as well as L2 regularization. So, what is this? This is 1 by 2n. So, your cost function is initially, means it is same as we have seen in case of ordinary least square, where we try to minimize sum of a square error. So, this is that cost function, but here we will add two terms, not only one term. So, one term corresponding to the L2 regularization. So, j is equal to 1 to m theta j square, and then another term corresponding to L1 regularization, j is equal to 1 to m mod of theta j. So, now what is we should talk about this lambda also that we added in both of these two cases. So, lambda is a, you can say, a hyperparameter, and its value will decide how much weight you are giving to the regularization term. If lambda is 0, it means we are not, we do not want regularization. Is the value of lambda is high, we are giving more strength to the regularization. In the same case here also. So, value of lambda will decide the strength of regularization. Now, in case of elastic net regularization, you see we, since it is combination of L1 as well as L2 regularization, and that is why there are two terms here, lambda 1 and lambda 2, and generally we say that lambda 1 is equal to alpha lambda, and lambda 2 is equal to 1 minus alpha lambda. So, basically in case of an elastic net, alpha and lambda, these are two hyperparameters, and value of alpha will decide strength of L1 and L2, basically trade off between L1 and L2, because if alpha is 0, in that case lambda 1 will become 0. So, lambda 1 will become 0, it means we will in our model we are not using L2 regularization, but if alpha is 0, then lambda 2 is lambda itself. So, it means we are having in our model L1 regularization. In the same case, if alpha is 1, in that case this lambda 1 will be 1. So, lambda 1 will be 1. So, we are giving weightage to the L2 regularization, but in that case 1 minus 1 will be 0. So, lambda 2 will be 0. So, when lambda 2 will be 0, so we are not giving, we are not having this penalty term, we are not having L1 regularization in our model. So, you can say that based on the value of alpha, you are giving weightage to L1 regularization or L2 regularization in your model. So, if value of alpha is, so value of alpha can be between 0 and 1, and its value will decide how much weightage you are given to which particular regularization. Now, what is lambda? So, lambda is nothing but lambda, when you will put here. So, lambda 1 is alpha lambda, and lambda 2 is also 1 minus alpha lambda. So, alpha is deciding which regularization you are giving more weightage, and lambda is giving overall weight to the regularization. So, how much regularization you need, based on that you will keep the value of lambda. So, again if it is 0, in that case you are not using any regularization in your model, and if its value is high, then you want regularization in your model. So, this is elastic net regularization. So, we have seen 3 types of regularization: L1 regularization, L2 regularization and elastic net regularization. Now, we will see the another important topic, that is evaluation of regression models, performances and their selection. So, we have seen many regularization models like simple linear regression, multiple linear regression, polynomial regression, and then decision tree, KNN, and there is SVM also we can use. So, in this course we will see how SVM is used for classification, but it can also be used for regression. So, now we know so many machine learning models that can be used for regression purpose, for solving the regression problem. So, we must have some way to evaluate these regression models. So, suppose for the given data set, to predict the value of response variables, we are using decision tree, we are using KNN, we are using multiple linear regression as well as polynomial regression. So, which model is working best in our case, or which is better? So, this we can do using R square metric, and that is R square, as well as we will see one more metric, that is adjusted R square. So, these are the two metrics that can be used for evaluating regression model performances, and based on that those values we can select the which model is the best model. So, what is R square? R square metric we will see here. So, you see suppose there is only two variable, y is the response variable, x is the independent variable or predictor. So, y is depending on this, and based on the scatter plot we can see there is a linear relationship, and suppose we are learning it through simple linear regression, this line is learned as a model. So, we can say that this is called as sum of a square residual. So, this is nothing but that we have seen till now as a j. So, j theta. So, j theta is equal to, we need to minimize sum of y minus y dash square or y minus y cap square, whatever you take. So, this is the actual value of response variable, this is the predicted value of response variable. So, we want to minimize this. So, after minimizing, suppose after doing this using either normal method or gradient descent method, you suppose learned this line, and there is another way to find this regression line. Suppose we take average of all these response variables values, and that we will take as the output of any for response variable value for any given instance. So, we have taken average of response variable value of all the instances in our data set, and that we will predict we will for any given new instance xi, we need to predict its response variable y. What we will give as an output? We will give y average. And how we got the y average? We have taken average of response variable value of all the instances. So, this is definitely not a good model, but in this case we can define what is the error term. So, in this is SS total, it is written as SS total. So, this is nothing but we need to minimize sum of y minus. So, here y prediction for all instances, how we are predicting response variable value, we are predicting it by y average. So, in both of these two cases, in this case where we are trying to minimize sum of y minus y cap or y dash, whatever the prediction error. So, using gradient descent or any way we will try to minimize this method, then the error, final error is suppose SS residual, and in this case this is the final error, that is SS total. Now, we can define R square as 1 minus SS residual upon SS total. So, this is the model that you have learned, and this is the average model. You can say that this model that is created in this way, this is suppose we are giving it name average model or average line. So, in this case SS total is the error. In this case whatever model will be learned, based on that you will get SS residual or the error term. So, how we are defining R square? R square is 1 minus SS residual upon SS total. So, what we can say, R square will be normally between 0 and 1. So, why it will be 0 between 0 and 1? Because we assume that the model that we have learned in that error will be always less than SS total. So, if this will be SS this error, average error. So, if this error is less than this, so in that case definitely 1 minus this some value will be less than 1, and in case when SS residual is 0, in that case R square is 1, and this is 0 when SS residual is same as SS total, then R square will be 0, because 1 minus and then SS residual is suppose SS is equal to SS total. So, we can say that R square's value will always be between 0 and 1. It can be negative also. When it will be negative? When SS residual is more than SS total, and there are less chance because SS total is this error. So, definitely whatever model we will learn, that will be better than this. So, SS residual will be less than SS total, but in some case when your model is working worst than this average line, in that case this can be this error can be greater than this error, and in that case R square can be negative also. So, now you can see R square is helping you to find whether your how much means your model is fitted to the data. So, R square if it is close to 1, in that case SS residual is close to 0, it means your model is well fitted, and if it is close to 0, in that case SS residual is greater than or large value. So, in that case your model is not good model. So, here it is written, if R square is 0, your fitted model is equally good as average line, because in that case SS residual, when it will be 0, we have already seen. So, this is SS residual is equal to SS total, then this will become 1 and then R square will be 0. So, in that case your model is equally good as only average line. And in case of when R square is 1, so in that this will happen when SS residual is 0. So, this is the ideal case, and R square is less than 0, it means your data is your model is worse than the average line. So, R square is the metric through that is giving the goodness of the fit. So, if its value is large, then you can say that your model is better. But there is one problem in R square, and because of that there is another metric, that is adjusted R square. So, we will see that in the next class, and today's lecture we have seen first of all different types of regularization methods that we can use in regression, and then we have seen R square metric, that is very important metric for evaluating all the different regression models. So, we will see what are the problems in R square, and then how it can be improved, and then we see what is adjusted R square. So, I am stopping here. Thank you.